Today I am going to discuss about COVID locked loops. Oh, sorry. It will be phase locked loop PLL. So why I have mentioned COVID locked loop, because in your surrounding throughout the day you were listening many things about COVID-19, and you were eagerly listening to the various events and mishap occurring during this period. Everyone is concerned about this. You and around your surrounding, your neighborhood, and national, international news. Everyone is involved about news or event related to COVID. So similar to this, in communication engineering, in every field, you will find a concern about PLL. PLL is the heart of communication engineering. One of the most important sub-circuit used in communication is PLL. This is similar to the circuit widely used in analog electronics, that is IC741 op-amp or IC555 timer, because it is widely used. Now let's start with what is PLL. Phase locked loop is a nonlinear negative feedback control system that locks the phase of a VCO to a reference signal. Okay, let me allow to explain that the meaning, the significance. Nonlinear, which doesn't obey superposition theorem. Okay, negative feedback. Negative feedback you have studied in analog electronics. Now, how to explain this negative feedback to a kid with blindfold? Okay, you have a piece of paper, white paper, there you put a dot with your pen and blindfold your eye. Can you touch the dot with blindfold? It's not possible. Why it is not possible? Because the movement of your fingertip is not controlled. You cannot see in which direction and how your fingertip is moving and how far it is away from the dot. So that means you cannot see the output so that you can control your hands or the movement of your fingertip. So negative feedback, in negative feedback phenomena, output controls input. This is the basic idea. So whenever you open the eye, you can measure the distance between your fingertip, direction from the dot accordingly. So you are measuring this thing, all this information through eye is sending information to your brain is sending control signal to your fingertip to move accordingly in order to touch the dot. This is how it is happening. So if you have to have some control over a process, negative feedback has to be there. This is the basic idea. Now application, the most important application is it is used in synchronous demodulation. Any modulation, it may be AM, DSB, SC, SSB, whatever may be the modulation technique, you can use PLL to demodulate the signal, demodulate any modulated signal. So this is just like Brahmastra for any receiver. And previous lecture I discussed about discriminators. So discriminator is cheap. Then why we should go for PLL, which is a costlier system? The important reason is that under noisy condition, that means when your signal is very low as compared to your surrounding noise, in that case you have to use PLL. So under low signal to noise ratio condition, the PLL is much more effective than your discriminator. So this is one of the important reasons of widespread use of PLL. Frequency synthesis. Uh, in last lecture, I told you frequency multipliers. Using PLL, you can multiply signal by any factor, in the which factor is a power of 2. It may be 4, it may be 8, it may be 16, 32, 64, 48, whatever may be. So that I am going to explain later on, but it is called synthesizer. That means you start with, let's say, 200 kilohertz. You can multiply it to 400, multiply it by 2, factor of 2 to get 400, or factor of 3 or 8. So you can multiply it by any factor to generate any frequency from our starting frequency. Okay, so this is the synthesizer operation. You know, electronic synthesizer, which is used for playing music and background scoring background music, they are using an instrument. The heart of that is PLL. So there you will find different keys. If you press different key, different sound will be generated. Different sound means different frequency will be generated. Heart is this thing. So it is done by using different multiplication factor. You different keys pressed means you are choosing different multiplication factor. Okay, so I'm not going to detail of that. Now PLL is said to be locked. This is very important operation when we will track the input signal frequency. That means the incoming signal frequency is WIN. It is said locked if PLL generates a frequency exactly equals to the incoming signal frequency. WIN equals to W out. W out is the frequency generated by the PLL. Okay. Now one point I want to mention, it is called phase locked loop, but still it is locking frequency. Why? The basic idea is, we know a rate of change of phase is frequency. Basically it is tracking phase to lock the frequency. That's why it is called phase lock loop. Instantaneous change of phase is tracked, thereby frequency is locked. Okay. Advantage, as I already mentioned, performs better than discriminators under noisy environment. There are various types of PLL depending upon its basic building block. I shall come to this later. Before that, let's come to this. It consists of three basic building blocks. Number one is voltage control oscillator. Number two is phase detector or phase comparator, and a loop filter, or basically low pass filter. Now with respect to these three blocks, it is divided, it can be of three types. Analog PLL, APLL, if the detector is analog mixer, just like balance modulator. Loop filter is RC filter, and controlled oscillator is VCO, whose control voltage is voltage. The control signal is voltage. Now another is digital PLL. If the phase detector is digital detector, I will show you what is digital detector. And loop filter is RC filter again, and control signal is for VCO is voltage. All digital filter which is now used, digital detector, and rather than RC, digital filter. You are not familiar with digital filter, you will study in maybe in 6th semester. And controlled, digitally controlled. Say, let's say we have a counter. Okay, counter will have some output, some counts, how many pulses it is, it will count. Now this count can be up and down. Using up down counter you have studied. Using a proper control signal, you can up count the value of the counter and down count the value. So this is digital control. Rather than an oscillator which you have studied, we are using a up down counter. This is the difference. But here we are concerned about only analog PLL. So this is the block diagram. This is the incoming signal. This is the multiplier or balance modulator or mixer, loop filter. Okay, the out of loop filter there is a control signal, a slowly varying DC E0T, which is in turn controlling voltage control oscillator. So in order to understand this thing, you just try to think event. Suppose a thief is running away and a police is running after him. So thief is running away and it is moving at his highest speed, and a police also, and definitely a fit police is running after him. So let's say after certain time, if he has the capability, it will capture the thief, and this phenomena, that means it will capture the thief when it is possible, when the velocity of thief and the velocity of police, they are exactly same, then they will this capture will occur. And once it is captured, once the thief is captured, he will try to uh, uh, get away from the police. So he will try to fight it out. Now if the capacity is there to hold the thief by the police, then he will catch hold of it and it will be retained. If he fails to do that, then the capture will be over. That means it is not locked, so he will move away. So the same phenomena is going to happen in case of PLL. So A sin omega t is as if the thief, and this is nothing but your police. So this is trying to capture this frequency. This signal frequency is going to be same as the incoming signal frequency or the reference frequency. Now let us discuss the um, individual blocks. First is voltage control oscillator. Normally oscillator frequency is fixed and you can vary the frequency of oscillation by changing its frequency determining network. In any oscillator there is a frequency determining network. Frequency determining network consists of either basically LC circuit or there may be RC circuit. If you vary one of these two parameters, either L or C, the frequency will vary. So you are varying the value of passive components. But in case of voltage control oscillator, it is such that you can vary the frequency not by varying its parameter, by varying a control voltage. So its output is a sinusoid, input is a DC. But whereas in case of oscillator, there is no control input. Only you can vary it using varying L and C. So we can write the frequency of VCO is proportional to some control voltage. Let's say it is proportional constant is kV. Now when E0T, the control voltage is 0, omega t, the frequency of the VCO is equals to omega c. This is called free running frequency. That is when there is no control signal, it is running with the frequency, it is the frequency of the VCO is called free running frequency. Okay, so if you integrate this thing, you will get the phase. So omega t is nothing but d theta by dt. So theta t will be proportional to kV integration of this thing. So I am omitting this constant part. I am just considering how it is varying. So it will be, if you integrate it, theta t will be equals to kV into integration of V0t. So this can be VCO. The mathematical form of VCO is nothing but an integration of phase. This is very important for mathematical modeling of VCO. Low pass filter. The low pass filter is a linear filter that smooths out the error signal E0T with gain constant Kf. Kf stands for, say, filter is a system which allows a certain band of frequency and reject a particular frequency range. So it allows a certain range of frequency, means its gain is high at those frequency. Rejects means its gain is low at those frequencies. So that's why allowed band, it is multiplied by a factor, let's say it is kf, and the band of frequency which is not allowed, the gain is 0. Now if you decrease, what is the use? Basically it decreases or increases the bandwidth of the whole system, that is PLL. You know, any low pass filter or high pass filter is characterized by its bandwidth. Bandwidth means a range of frequencies allowed by the filter. Now, so this frequency low pass, let's say low pass filter whose bandwidth or cutoff frequency can be varied by varying its circuit parameter. If it is RC circuit, if you vary the value of R and C, its cutoff frequency varies. Now suppose so what is the cutoff frequency? FC equals to 1 by 2 pi into RC. 1 by 2 pi into RC. Cutoff frequency, RC is time, it will be 2 pi by T, that is 2 pi into 1 by RC. This is the cutoff frequency. So if you want to increase cutoff frequency, then R or C should be reduced. If you want to increase cutoff frequency, R or C value should be decreased. This is the basic idea of low pass filter. Now this low pass filter controls the bandwidth. This PLL is also a sort of filter whose bandwidth can be tuned, bandwidth can be varied, or you know, any bandwidth has a center frequency can be varied. Now if you decrease the bandwidth of low pass filter, that is in that case the capturing process will be slowed down. That means the police is not fit enough, so your speed is slowed down. Or here equivalently, if the bandwidth of the low pass filter increase, it will be slowed down, capture will be slow, it may not be possible to capture the incoming signal frequency. Or if you make it if you reduce the low pass filter bandwidth, so capture will be faster, but it has got some other problem I will discuss later on. So decreasing will increase the bandwidth or decrease the bandwidth, and the capture will be slower or faster. So in that case it will decrease or increase the capture range, that I will explain later on. Now once it is locked, greater immunity to higher frequency interference. If the bandwidth of low pass filter is narrow, then narrow means bandwidth is less, it is not going to allow higher frequencies beyond this particular range, so it will reject the higher frequencies. So this is one of the advantages. Narrower the bandwidth, more rejection of interference or high frequency signals. But how to decide whether it will be narrower or it will be higher or it will be lower? So it will be decided by other factors, because PLL is such a system. Using this single topic, a total book can be written. There are various books only written on this particular topic are there. It's not so easy. It involves control theory, many mathematical treatments are there, so you will not be able to grasp it totally, but simply I am going to explain with your whatever knowledge you have gathered so far. Another part is phase detector. Phase detector is nothing but balance modulator, which will multiply these two signal with a filter. So let's say the input signal to the phase detector is A sin omega ct plus theta I, theta is phase angle, and VCO output be sinusoid 2b cos omega ct theta 0. You might ask why I have taken 2b. Why not b? You can take b, but it is used to simplify the calculation. Now the thing is that why I have taken cos, or I could have taken both sine or both sine, both cos, or any combination of combination thereof. So this will be explained after you go through this calculation. A multiplier output will be 2ab. Now you have taken 2, that's why you can resolve into 2 sum term and difference term, sine cosine, so it will be sine sine, isn't it? So the last term is higher frequency and this is low frequency. 2 omega, omega is absent. You have assumed that the loop is under locked condition, that means frequency is same but phase is varying. Okay, so it is phase locked loop. Let's see what happens. So if this signal is passed through a low pass filter, the output E0 will be AB sine theta e minus theta 0 or sine theta e. Theta e is called error signal. Theta e is equals to theta I minus theta 0. That is the difference between phase of incoming signal and phase of the signal generated by the VCO. So we can write it AB theta e if, okay, if theta e, oh I have missed one thing, if theta e is very small, you can write E0 is almost equals to AB theta e. So E0, what I have said, phase detector, that means output voltage is proportional to the phase of difference of phase, so that's why it is called phase detector. Now phase detector constant is defined as the E0 by theta e, that is AB. Okay, and okay, while we assume theta e nearly equals to 0, PL assumed to be linear, so that's why we have written okay, it will be AB sine theta e. AB is missing. Oh, small printing mistakes are there, you must forgive me for this. Now with these two basic building blocks, I am not going to explain low pass filter, the structure of this thing. It is RC filter, let us assume. The operation of PLL. Operation of PLL can be thought of three different processes. Number one is free running. That means there is no incoming signal, then no thief is running, so that's why the police is sitting idle at his office, Thana. So he is taking a good nap. Now suddenly incoming signal is applied. So incoming signal may be IFM or PM. Let's see what happens. Then capture process I have already explained. The range of input frequency for which an initially unlocked loop will be locked. Range of frequencies, that means it depends upon the frequency of the incoming signal. If it is very high speed, then the VCO may not be able to, definitely it will not be able to capture the frequency. And even if it is very slow, it is not possible. A human can do, but a VCO or an oscillator cannot reduce its frequency beyond a particular value. So it has got limitation. So it can vary over a range. If the incoming signal frequency is within that range, then it will be able to capture. Okay. Lock range. Now, once the police is got hold of the thief, it depends upon the capability of the or the strength of the police, how far it will be able to, how long it will be able to got hold of the thief. So same thing. So if the incoming frequency varies the VCO frequency will remain matched with the incoming signal frequency. Suppose incoming signal is increasing, VCO frequency will be increased to that value to match that. So how long it will continue? It will continue up to a certain value. Similarly, if the incoming signal frequency decreases, then VCO frequency will decrease. How long it will be able to catch this this decreasing frequency? There is a limit. So there is a limit at the lowest range, at the lower value, as well as at the higher value. So you see, so lock range, it has got a lower value, higher value. Similarly, capture has got a lower value and a higher value. And capture range is different from lock range. That I am going to explain, because lock range depends upon certain factors and capture range depends upon some other factors. Since the factors are different, the ranges are different. I told you capture range depends upon the low pass filter, but lock range depends upon the factor of the phase detector, the factor of the VCO, and the factor of the low pass filter. All three. Factor means I have already defined the factor for this thing. So what is that? For KV, factor of VCO, then factor of low pass filter, that is KF, KV, and this is KD. KD is the factor of the phase detector. These three factors. It depends upon these three factors, whereas capture range depends upon the bandwidth. Okay. So in a nutshell, lock range depends upon the gain factors of the phase detector, gain factor of the low pass filter, and the gain factor of the VCO, whereas capture range depends upon the bandwidth of the low pass filter. This is the important information. The PLL is said to be locked if the frequency of the input signal is exactly equal to the VCO frequency. In other constant, theta is constant under such condition. Now, these are the important point. If incoming signal frequency is increased from omega c to omega c plus k, let's say k is some value, then theta I increases to theta I plus kt. K, omega t is the phase, omega c into t will be phase. Similarly, k is in radians multiplied by t. So theta I will be increased to theta I plus kt. Accordingly, theta e will increase accordingly to a new value, let's say E0 dashed. This in turn will adjust the VCO frequency, since you know E0 is the control input to the VCO. And similarly, if incoming signal is decreased, the loop will acquire lock by adjusting E0. Okay. Once the loop is locked, the lock range is determined by open loop gain. The factor, the product of KD, KF and KV that I have already explained is known as open loop gain, that you have studied in feedback system in analog electronics. On a locked condition, that is when incoming signal frequency is unlocked condition, incoming signal frequency is different from VCO frequency. If the difference frequency is more than the cutoff frequency, let's say cutoff frequency is 3 kHz. If the difference of incoming signal frequency and VCO frequency is more than 3, then it will not be allowed by the low pass filter. So 3 kHz is the bandwidth of low pass filter, but this difference frequency becomes, let's say, 5 kHz. So it will not be able to capture. So under this condition, this will cause the loop to remain unlocked. If the difference frequency approaches filter bandwidth. That is, let's say 3 kHz is the low pass filter bandwidth and the difference frequency is approaching 3 kHz. Then the speed of these two will try to match police and thief, the same event I am going to as a reference. So if within the capability, then it will acquire the thief, so loop will be locked or acquisition will be there. Difference frequency is reduced further, will enhance the tendency of acquiring lock. So if you reduce it, so if it is within the bandwidth, let's say difference frequency, that is the difference between the incoming signal frequency and the VCO frequency is decreased. Let's say it is 1 kHz, then it will easily acquire the lock. Finally, how PLL demodulates FM. Let's the input to the phase detector is FM A sine omega ct theta I equals to this, you know, and VCO output be a sinusoid B cos omega ct. Then since it is a phase lock loop, we are considering only phase part. Okay, so theta is the phase for this and theta 0 t is the phase of the phase detector. Integrator, I have already explained, is the mathematical model of VCO. Then theta e, sine of theta e, it is passed through a low pass filter. Okay, and so this is equals to theta 0 t dot is equals to CE0 t. Why? Because if you change the control signal, then frequency will be changed. That is the basic idea of VCO. Definitely E0 t should be theta 0 dot theta e dot by theta 0 that is its phase. Theta 0 dot means d theta 0 by dt, that is the frequency, instantaneous frequency of the VCO. It should be a function of control voltage. Okay, so its output should be matched with this. Now see, we have a VCO instantaneous frequency is theta 0 dot t, that is equals to kV into E0 t. Kv is the constant of VCO, or E0 t equals to theta 0 dot divided by kV, where kV is the constant of VCO. I have already mentioned. Now, we know that the output from the phase detector is proportional to theta e, that is theta e equals to theta e minus theta 0, that is theta e equals to this thing for FM and theta 0, phase of the VCO, or theta 0 equals to this minus theta e. Okay, then E0 t is equals to theta 0 for VCO. E0 t control voltage equals to theta 0 dot divided by kV. Okay, and if you substitute this, you will be kf by kV into mt from here. Okay, theta 0 equals to this one, kV. You substitute this theta 0 dot from here. So it will be kf by kV into mt. So E0 t, the error signal of VCO, is proportional to mt. Assuming, now if you differentiate theta 0 t, what you will get? Theta 0 dot will be kf into mt. Okay, so substitute that kf into mt here, so kf by kv into mt. Now here we assume theta e is very small, so you see theta E0 t equals to theta kf by kv into mt. The control signal to the VCO is proportional to mt. So mt, the control signal to VCO is nothing but demodulated FM. Okay, so this is how it is. FM is demodulated. Similarly for PM, theta I equals to kpmt. E02 can be similarly derived as Kp by Kv into m dot t. So because here theta 0 dot will be Kp into mt, so theta 0 dot will be differentiation of that will be Kp into m dot t. So you will get this one. So this is how PLL can demodulate FM and PM. Okay, thank you.